But nevertheless, we can talk about having a slope to a line that's tangent to any point along here. And sometimes that's useful if you're dealing with some type of mechanical system or some type of biological system. Sometimes you want to find rates of change. Think about inside of a car engine, you have these cams, you know, that lift the valves, and these cams are kind of oval shaped, and they lift the rods as they rotate. You want to know how fast that rod is being lifted or let down. And so in a lot of engineering applications, you get these kinds of relations that aren't necessarily functions. But what we can do is we can determine the slopes of these not really functions, relations. We can do this by a process known as implicit differentiation. And we don't have to really enter any new rules to do this. We just have to take a little different view about how we differentiate. Now, oftentimes, especially with one that's not a function, you'll have to know both x and y in order to get what that slope is, because obviously for any given x you can have more than one y. So we'll see how that works out and what we can do about things. So I'm going to start using notation that's a little different than this prime notation with the functions, because we're not dealing with functions anymore. So when I'm going to differentiate like both sides of a relation, I'll either use this notation, the d dx, indicating that I'm differentiating with respect to x, or I'll be just using y prime to indicate the derivative of y. Okay? So we go over all the rules that we know. The derivative of x squared, of course, is just 2x. That's the power rule. So if I take the derivative of y, okay, let's say this y is in an equation, all I'm going to get is dy dx, right? That's or I can indicate that as y prime. Now let's say I have a little bit more complicated type of expression in y. So what do you suppose the derivative of y squared is? Now x squared, the derivative is 2x. But we're differentiating this with respect to x, not y. So it's going to be a little bit more than just 2y. It's going to be 2y times the derivative of y. Think about the chain rule here. When I take the derivative of y squared, I'm going to use the outer function as the squared, and the inner function is just y. Okay, so when I take the derivative of y squared, I get 2y dx dy, or dy dx. I said that backwards. Okay, so this is probably the most difficult part about implicit differentiation, is that we have to remember that when we take the derivative of anything that involves y, all the rules apply, but the chain rule always applies to the point where you're going to have that derivative of y as the last factor. So if we have something like the derivative of xy, both the product rule and the chain rule come in here. Okay, so the first derivative is going to be the derivative of x with respect to x. And of course that's 1, right? The derivative of x is 1. I'm just writing this out so you can see it more explicitly. Times y. And then the other part of the product rule is that I'm going to take x times the derivative of y. And so when I simplify this out, I get y plus x times dy dx.
And then what about the chain rule? Is there another step after that?
No, you've completely differentiated y. The derivative of y is dy. dy dx. Okay, so it's the product rule here that I'm using. Okay, so let me give a full-blown example here. You recognize what this is, right? It's a circle. Circle with radius 5. Okay, so I'll draw a circle, graph it, and so I'm going to be interested in the point 4, comma 3, right? 4 squared plus 3 squared is 25, and the square root of 25 is 5. So you know that 4, 3 lies on that circle. And I'm going to try and calculate what the derivative of this thing is. Now, we can probably just eyeball it at this point. We know that the line has a negative slope, right? And we know it's going to be perpendicular to the line that goes from the center of that circle to the point 4, 3. So you would think then that since it's rising 3 and running 4, that line, since it's perpendicular, is going to be negative 3/4. Okay, because that's the negative reciprocal of the line that's going out from the origin to that point. So let's calculate it explicitly and see what we get. So here's my notation where I'm going to use that d dx. I'm going to apply it to both sides. And then, of course, with products of derivatives, I can separate those out into two derivatives. And then, of course, d dx of 25, the derivative of a constant is 0. And so then I'm going to take the derivative of these, and I get 2x is the derivative of x squared. The derivative of y squared is going to be 2y dy dx. So there's that chain rule. The derivative of y squared, the outer function is squared, so I take 2y. The derivative of y then, from the chain rule, you use the inner function, which is y, is going to be dy dx. And that, of course, is 0. So this is kind of an implicit statement of what the derivative is. Now we're going to just solve for the derivative. And so I'm going to bring the 2x over to one side. I'm going to divide both sides by 2y, and I get negative x over y. Okay, so there's the derivative of that circle. Now notice the derivative involves both x and y. And this is something you really want, because we don't have a function. We just can't use a single value to compute any derivative, because we have to know, is it going to be in the upper half of the circle or in the lower half of the circle? And so then that y becomes important. So if I plug in what I know, my x is 4, my y is 3, and so I get negative 4/3. I think I said 3/4 at the beginning, and maybe I had my x and my y switched around. It rises 3 and runs 4, so this is going to be 4/3, which is the reciprocal of 3/4. We take the negative of that. So it's what we would expect if we just thought about it from the standpoint of trying to derive it from simply the geometry of the graph. Now, if I take the derivative at 4 and negative 3, okay, so the x value is the same, but I'm on the lower half of the circle, so my y value is going to be negative 3. The derivative there is going to be 4/3. And that's what it looks like, right? You take negative x, which is 4, over y, which is negative 3, and we get 4/3, and it's positive. So it's not really the reciprocal of the other line. You can see that as we get closer and closer out to x equals 5, that these lines become steeper, both negative and positive. If we went back out to x equals 0 and y equals 5 or negative 5, then we get a slope of 0, which is right at the top of the circle, what you would expect. Okay, so this function should feel, or this relation should feel right in terms of its derivative. And so the derivative, when you're starting to take it, looks kind of funny occasionally, but all you have to do with this thing is just apply the rules that you know, principally the product rule and the chain rule, absolutely blindly, and remember to always use the chain rule when you're dealing with y, because you not only have to take the derivative of whatever we're doing to y, we have to take the derivative of y as well. Yes?
So does it matter which line the y is, or is it kind of like slope, in that you could use either one as long as you're consistent?
Well, it matters a lot which y it is, because we have two different slopes.
Okay.
See, that circle is a relation, it's not a function, right? It fails the vertical line test. And so when we say x equals 3, we have two possible values for y. And so which value am I really looking for the slope on? If I'm looking for the one that y is 3, then my slope is negative 4/3. If I look at where my y value is negative 3, then I get a positive slope, 4/3. And so this happens with these implicit differentiations, that if we don't start out with a function, we likely don't end up with a function. We have something that we have to choose which x and y do we have? Now, of course, we can solve x squared plus y squared equals 25, and we can get, if we plug in an x, we can get two values of y, and so, you know, that's how we would arrive sometimes at both y's. But when we're actually evaluating it, we have to choose which ones we're going to use. Now, I wrote this out dy dx at 4.3 as just an ordinary way to write this. You'll see occasionally where if you take the derivative, you'll draw a vertical line, and you might see something like x equals 4, and you might even want to see y equals 3, something like that. That means it's the derivative evaluated at those values. Now, if we have a simple function, occasionally you'll just see a single, you know, value here like that, and that would mean that we're going to evaluate this at x equals 4. But in this case, we would have to specify both x and y, because any given x doesn't lead us to exactly one y. Okay, so let me give you another example. This is the first one that I showed you. That's that thing that looks like an omega. And so I'm going to take the derivative of this. I'll mark both sides d dx to indicate that I'm actually taking the derivative. And now I'm not going to bother to write each individual term of d dx. I'm just going to take the derivative of each individual term. So the first term is going to be 2x, right? The derivative of x squared is 2x. The derivative of the second term is 3y squared, and then the chain rule says you have to take the derivative of y, and so you get dy dx. And then we have negative 2y, so the derivative of that is just going to be negative 2 dy dx. And then, of course, on the other side we have 0, because the derivative of any constant is 0. Okay, I do want to find dy dx. And so we have, this will start to feel like it falls into a certain pattern once you start doing these. So the first thing you want to do is you want to bring all of the terms that don't involve dy dx to the other side of the equation, or to one side of the equation, keeping all the terms that involve dy dx on one side. And then the magic step here is that we're going to factor out dy dx. And so we have now a factor times dy dx, and if we divide both sides by that factor, we get what our derivative is. And so this will be pretty common sight, that you have your derivative equals some expression, oftentimes a ratio involving x and y. Okay, so let's move on. I'm sorry?
Is that negative 2x or is that a 1?
That's negative 2x, right? Because it comes from here. This 2x gets moved onto this side. And so, yeah, I didn't write that very clearly. That is 2x right there.
Before you go to the next slide, so I have to admit this particular kind of notation still kind of confuses me a lot. But it looks like at the end of the day, the whole point is to be able to factor it out so that the dy dx is always on one side. On the other hand, it kind of acts like something you multiply by. What the? Do you ever actually multiply by it?
Multiply by?
Like, so you factored it, or yeah, you factored it
Factored it
out
out.
over there, the dy dx, so that it's on one side, so that it becomes, you know, it solves the equation. But it also acts like a factor. Is it ever used as like a factor?
You want to do something like this?
No, I don't. I don't want to.
No, but I mean, is this what you're getting at, to have something that looks like this?
Yeah, probably.
Yeah, okay. That's when we're separating it out into individual differentials, and we'll get to that. Okay? We'll get to that probably
So
earlier than you want to.
Become like it starts to actually have an active role. Okay.
Yes. But right now it just means the derivative of y with respect to x. Okay, so here's some strategies to use when you're doing these. Okay, the first thing is you may use y prime instead of dy dx. And this will simplify your notation quite a bit. Okay, seeing dy dx, that's a whole lot of writing. Y prime is a little easier to get to. Okay, so if you start with a rational equation, put it into the form of a polynomial. And so what I mean by that is, if you have something like this, it's possible to do this implicitly, and you would end up using the quotient rule with the product rule with the chain rule. So if you multiply both sides by x over y, you get something that looks a little bit more like a polynomial, right? I mean, strictly speaking, we've been dealing with polynomials with integer exponents and in one variable, but put it in a term that it's just the sum of terms, a sum or differences of terms, if you can. Sometimes you can't always, but if you can get it to this shape, it will almost always simplify things for you, and it's an equivalent expression, so you don't have to really worry about anything. X and y can't be zeros, so we do have a domain restriction in there, but that will, considering that will come later. So of course we're going to use the product and chain rules, and so the thing that you have to concentrate on is making sure that you treat y properly. And so I'm going to differentiate that. So look, if I go through that x plus y equals 4xy, the derivative of x is just 1. So I start with 1. The derivative of y is just y prime. Then I have 4xy, and so what I'm going to do is I'm going to use the product rule here. So the first thing I do is I take 4xy, take the derivative of x, and that becomes 1 times y, so I get the 4y. Remember, the coefficient just rides along. And then in the second term, I'm going to take the derivative of y times x, and so I get 4xy prime. Okay, so now I have these four terms. And then I want to move all the terms with y prime to one side, everything else to the other. All right, so let me do that. So I'm going to move that 4xy prime to the left, and I'm going to move over that 1 to the right. And so I get this. And so now I factor and solve for y prime. So in this case, it's going to be 1 minus 4x times y prime equals 4y minus 1. And there we get y prime equals 4y minus 1 over 1 minus 4x. So this means now that if I take any point of that graph, I can have an x and a y, and I can calculate the slope at that point then. So this, even though it seems perhaps kind of unusual to have y in the expression for y prime, it actually works out pretty well once you evaluate x and y. Okay. So let's do this one and use the y prime notation. All right. So the first step then is take the derivative of xy. So we take the derivative of x times y, and then x times the derivative of y. So there's our product rule for the first term. And then the derivative of 2y is going to be 2y y prime. Right? That's the chain rule. And then we take the derivative of x squared, and we get 2x. Now notice you'll never ever have an x prime in there, unless you're taking the derivative with respect to t or some other variable. because the derivative of x is just 1. And so even if you insisted on using the chain rule of x squared, you'd still end up with just 2x. Okay, I move that y over to the right side. I factor out the y prime. And then I divide by the factor that's in front of the y prime. And there's my answer. So it doesn't look too different from that last one. You know, it was a similar kind of expression. Okay, there's 4 of you texting right now. I'd like you to stop, okay?
Why is the first y on the second line totally separate? I understand you got the 2y, that makes sense, and the other one on the other side. Where's the first y?
Think of the product rule. If we take,
Oh, okay.
this is going to be f prime g plus f g prime. And so if this is xy, I'm going to have the derivative of this times y, 1 times y,
Okay.
plus x times the derivative of y.
Okay.
Okay? Y'all following? Ready to try one yourself?
Can I get the answer from the last one?
Thanks. Okay, go ahead and try this. Before you start, what does this graph, what kind of shape is this? It's a x squared minus y squared. So what is it? It's a hyperbola. Okay?
Thank you.
Oh, yeah. Oh, wait, I don't
Okay, how'd you do on it? All right? So, take the derivative of x squared minus y squared, so we get 2x minus 2y, y prime. And so we get something very similar to what we had with the circle, except now the y's or the negatives will cancel out ultimately, and we'll get the derivative, the slope equals x over y. Now, here's a graph. I just wrote it on the board while you were working on this. Here's a graph of the hyperbola. And I don't know that a lot of you, at least since you've been here, I don't think I cover this in Math 12, but graphing a hyperbola has asymptotes, these slant asymptotes. And with this particular one, this x squared minus y squared equals 4, this asymptote is, has a slope of 1, and this one has a slope of -1. And so think about the long-range behavior of this thing. As x goes to infinity, okay, then y gets infinitely large, but the slope of this thing comes really close to the asymptote, which is 1. So if x equals 1,000, y equals something slightly different than 1,000, but pretty close to 1,000, and you're going to have that slope, the ultimate limit of that thing is going to be equal to 1. Similarly, if we choose to go on the negative side, then we'll get negative 1. Okay, so try another one, a little bit harder. X squared y squared minus 2x equals 4 minus 4y. Okay, so product rule. We take the derivative of x squared, which is 2x, and multiply it by y squared. And then we're going to add that to x squared times the derivative of y squared, which is 2y y prime. And then the derivative of negative 2x is just negative 2. The derivative of 4 is 0. The derivative of negative 4y is negative 4y prime. Okay, so now I'm going to rearrange it so I have all my y primes on one side and everything else on the other. So I bring that 4y prime, that negative 4y prime to the left and becomes positive. And then I'm going to take that 2xy squared, move it to the other side, and it becomes negative. And now I factor out my y prime. The other side stays the same. And now I divide by that factor that's in front of y prime, and I get my answer. Everybody follow on this? This takes a bit of practice, no doubt. Okay, so here's another one. They get worse. Not too much worse. Okay, it's real close to the end of class, so let me walk you through this one. But think about how you would handle this. You have the square root of xy. Now you have two choices here. You can take the derivative of the square root of xy using first the chain rule, or you can recognize that the square root of xy is the same thing as square root of x times the square root of y. Now I may have the chain rule on the y side, but I don't have it on the x side anymore. I have the product rule that I can use. So here's one of these things that can take multiple routes. You could have done that, taken the derivative directly of that square root, and then you end up with, by the chain rule, then you take the derivative of xy. Or you can separate it out into two factors. And so if I then take the derivative of this, I get, by the product rule, see this 1/2 x squared right here is going to be the derivative of square root of x, and that's times y, or square root of y. And then I'm going to keep the square root of x and multiply it by the derivative of the square root of y, which is 1/2 y to the minus 1/2. And then the chain rule says I have a y prime after that. And then the next term, the derivative of negative 4y y squared, negative 4y squared, right. And that's going to be negative 8y y prime, and the derivative of 12 is 0. So let me rewrite it to hopefully make it look a little bit simpler. Now I do have that one term that I need to bring over to the right side, so then I can factor out my y primes. And then I'm going to take the ratio of those two, and there's my answer. Now, if you are using Wolfram Alpha to check your answers, I guarantee you they will come up with expressions that are different than this, because their sense of what makes a simple function is way different than your sense of, and my sense of what makes a simple function. So you do have a lot of variation in the forms of these things, and if it's simple, like combining like terms and stuff like that, do it. I wouldn't go any further than this, okay? The only thing that it'll do for you is it'll give you an opportunity to make an algebra mistake. but certainly this is going to be sufficient for anything that I'm going to ask you to do. So, whew, that one's done. All right? And that's about as hard as they get. Okay, so